Thank you, Marika, for the introduction. Thank you all for attending this webinar on seismic data QC, attributes, filters, and testing. OpendTect is a perfect tool for investigating seismic data characteristics, applying filters for improvements in signal-noise ratio, fault fidelity, and other seismic qualities. Also, OpendTect has an ideal interactive environment for testing filters and attributes, so we can customize the workflows to characterize the to the characteristics of the particular seismic survey we're working with. The 20 minutes of this webinar are not enough to show more than a few of the available workflows and tools for these purposes, but I will give you a taste of what can be done. So let's start fast and furious. What I often see is that users do when they get access to a tool, whether it's a filter or an attribute, is that they hurry to the application without giving much thought to the data characteristics or how the tool works. So I first want to take a step back and show a few of the many tools that can be used for data investigation. A few of the things I'm interested in at the initial stage of an interpretation project are amplitude ranges, frequency spectra, phase, signal and noise ratio, all through the survey area. We can examine these, for example, using the OpendTect well-time module. But in the next example, I will focus on establishing a quick impression of the lateral and temporal variability of only the amplitude and frequency character throughout the dataset I use for the demo. I have here an inline for initial inspection. I can actually move this inline quite conveniently through the data. It's quick because all data is loaded in the random access memory. I can manipulate the inline section to only cover the shallow section of the data, and then I can investigate this section of the data at this location. For example, I can look at the histogram, look if in the histogram there are any odd features, which in this case would be the excess of zeros here, which is related probably to the very shallow data that is being muted out. Also, I can investigate the value range, the mean, and the standard deviation, and check if these are stable throughout the survey. I can as well look at the amplitude spectra, the frequency spectra, look at the particular shape and characteristics of the spectra, see if I see any peculiarities in it, and observe the bandwidth. I can then reshape this panel to only cover the deeper part of the data and do the same investigation. I will only show it here for the frequency spectra. I can then move to a new spot and repeat this QC and see if I find any areas in the dataset that are out of the ordinary. It's also convenient or instructive to review trends in the dataset. I've done this here by plotting the frequency spectra at different inline positions from left to right, and from top to bottom going for the shallow data extraction to the deep data extraction. Here we see that the frequency spectrum is very stable against position, with very similar spectra extracted at different inline sections. We see that there's a systematic difference in frequency content between the shallow and the deep section, with a loss of high frequencies in the deeper section. It's important to know how the data changes vertically and laterally. For example, to determine the optimal time gate in terms of seismic loops, or whether different depths or zones maybe need different attribute settings because the data characteristics have changed too much. I will now go back to OpendTect and show how you can use attributes and straight slicing to improve the 3D understanding of the data characteristics more. This is the random line I use for testing. It runs from corner to corner in the dataset, and it samples a number of geophysical and geological interesting zones, including a faulted zone, a low amplitude zone, and a more continuous zone. First I will have a look at the RMS amplitude attribute. I don't see any obvious data artifacts on this attribute. What I do observe is that there's a significant low amplitude zone, which I have to keep in mind because that might be a zone with lower signal to noise ratios. I will then investigate the average frequency attribute. We see that here to the right we have a patch of data where the average frequencies seem to be decreased compared with the rest of the data. Also, we see that the average frequencies in the shallow section are significantly higher, around values of 55 to 60, than the deeper section where they have values around 30 to 35. That is a very sudden and strong decrease of the frequency. When we investigate it more, we see that that sudden decrease in frequency is related to this very fragmented reflector. This might be a geological phenomenon, or might be an interaction of the geology with the seismic processing, or a combination of both, causing this frequency loss. Knowing now one section view, I will develop an interval slice view of the same attributes. I will refrain from the actual calculations to create these maps, but I'll first show where the straight slicing tool needed to make these maps can be accessed. Go to processing, create horizon output, straight amplitude. There one can select a single horizon and a time interval or a double horizon. Input volumes or attributes, and output a statistical quality of those volumes within that interval. In this case we use mostly average and RMS. We'll first investigate the shallow section. Here I have plotted the RMS amplitudes taken from this horizon to the top of the data. We see some shapes clearly related to geology. This shape is related to shallow gas. Here are some shapes related to the faulting in this area. But we see also a number of data artifacts. We see that this patch looks slightly different, and we see banding. If we do the same for the average frequency attribute, so we here have the average of the average frequency attribute, we see more data artifacts. We see that this patch now really stands out as a low frequency patch, suggesting that this piece of the data is possibly merged in from another or older survey into this dataset. We see strong banding, and we see also a decrease of frequency content from the west side to the east side, suggesting that this data possibly might not be stationary. So we will do the same investigation on the deeper level. First looking at the RMS amplitude extracted from this horizon to the level indicated by this white horizon here. Here we see almost exclusively shapes related to geology. We see here something related to diaparism. We see faulting patterns. And here the lower amplitudes might be related to the presence of shallow gas above this section. This patch that we saw earlier is not visible on the amplitude extraction. However, if we go to the frequency extraction, we clearly see this patch standing out again. So this would be an area that we cannot treat in the same way as the rest of the data. We see also shapes related to geology, attenuation due to the shallow gas. We see that the decrease of frequency from the west side to the east side is not visible in the deeper section, so that's not longer a concern. But we continue to see banding in the seismic attribute. So I have been analyzing the data for approximately 10 minutes now, and I already have established a good understanding of the 3D characteristics of the data and pinpointed some possible problems, of which the acquisition footprint is possibly the strongest or the most urgent problem to address. Now I will go back and review the extraction of the seismic amplitude at a shallow horizon. We see the same bending as we saw on the frequency attribute extraction earlier. This bending, when you measure it, is actually quite wide, around 300 meters or 12 bins, which makes it hard to attack it with basic filters. Instead, I will use a filter created by a third-party vendor, Estimage, called the Destriping plugin. This is a filter that uses factorial kriging, which is a concept based on the statistics of the data. More precisely, it uses that the lateral correlation of the amplitudes due to geological factors is different than the periodic lateral correlation created by the footprint. This enables the filter to separate signal and noise. There are only a few parameters that this filter needs, so it's simple to operate. The user has to give the footprint width, which is the half of the before mentioned 300 meters, and the footprint orientation, along inline or along crossline. The filter can be applied repeatedly for footprint signatures with varying orientation or periods. I will not calculate the filter itself right now, but simply show you the before and after amplitude extraction. So this is the original data, and this is the same amplitude extraction after applying the Destriping filter. One sees that not all, but most of the acquisition footprint has been removed by this filter. When we zoom in, we see a remaining effect of lateral high frequency wiggling in the data. The Destriping filter has attacked striping with higher periodicities, and the small scale variation is still present in the data. I will now progress showing a few simple and then one more advanced seismic filter in OpendTect that actually addresses this high frequency noise. Let me clean up the OpendTect visual scene a bit and focus ourselves on an interesting part of the testing random line. First, I will show a structurally oriented averaging filter. Structurally oriented means that the averaging operator is applied with the correction for seismic dips when stepping out. So it will follow the reflector even if the reflector is dipping. A strong averaging filter may be advantageous to create a volume that is more convenient for seismic horizon interpretation. However, it will smear outliers and may create continuity where there is none. This is the averaging filter with the 3x3 step out. It indeed improves the interpretability and the possibility to use horizon trackers in this low amplitude noisy zones. But in this faulted zone with higher signal to noise ratio, it does not do a good job and it creates a lot of continuity. An alternative is the same filter setup, but replacing the averaging operator with the median operator. The median operator has better characteristics in removing outliers, and it has better edge preserving characteristics. So this is the same filter, but then with the median operator. A wink, average filter, median filter, average filter, median filter. One sees that in this section the median filter and the average filter gives almost the same result. However, the faulting, the deep faulting, is better preserved in the median filter, which we see now. I was speaking about Stepout, and actually the Stepout is one of the most important, or the most important parameter that determines the strength of the filtering. So that is something that as a user you wish to test. OpendTect has great interactive tools for this. I will show how we test the Stepout for this median filter. We will calculate now this median filter on the random line 5 times. The first one with Stepout 0, basically copying the data. The final one with Stepout 4, the strongest filter setting. We can use the slider and we can see the effect of the Stepout on the filter output. This interactive evaluation is one way to optimize the filter parameter settings. Something else we want to look at are the noise characteristics, or the residue of the filter. This is the residue of the original setting of the median dip filter with the original setting, and it shows what has been removed by the filter in the data. And this looks indeed fairly random. Again, one can, apologies for the operator error there, one can investigate the effect of Stepout on the filter residue. Here the filter is again calculated 5 times with a Stepout from 0 to 4, but now the filter is subtracted from the original data, and we'll see the noise levels, or better residues, filter residues, for weaker and stronger filters. So filter of Stepout 1, Stepout 2, Stepout 3, Stepout 4. And at a certain point one might decide that the residue does not just represent noise, but that actually valuable signal is removed. So this is also a great evaluation tool to see what is the optimal filter setting. This median filter is one of the workhorses in OpendTect, and there is a predefined median filter available in a default DGB attribute set that's included with the OpendTect software release. So a user can start applying this filter without too much effort or learning beforehand. It is obvious that both filters, averaging and median filter, do a good job removing the lateral highly variable noise, as we see in this residue. However, both median and averaging filter causes some degree of averaging of what are possible real discontinuities over real fault planes. In OpendTect there are various filters available that combine a smoothing filter on the reflection events with edge enhancing filter with an edge enhancing filter at fault discontinuities. Here I will demonstrate the use of the edge preserving smoothing filter. This filter is found in the Faults and Fractures plugin, particularly here. I will not demonstrate the parameterization of the filter, but show the effect of the application of this filter. So here again we see the original data, and this is the output of the edge preserving smoothing filter. One sees that the high frequency wiggling has been largely or completely removed, but at the same time the fault planes here are actually enhanced and more clearly visible. I've applied this filter twice. The first time that we see here, it's applied with weaker settings. I've applied it the second time with stronger settings. If I compare these two filters, I personally, and this is to some level subjectively, I like the weaker filter better in this lower, higher signal to noise ratio setting, because it preserves stratigraphic variation in the amplitude and frequency characteristics. However, in this low amplitude, low signal to noise setting, I actually prefer the stronger filter. The stronger filter allows me to better see stratigraphic relationships such as on-lap, and it might just eke out some very subtle faulting that crosses this section. So I like to combine the best of two worlds, and I will show you how to stratigraphically combine two different filters. First of all, I have interpreted this horizon deep separator, called deep separator, between the lower high signal to noise section and the shallower lower signal to noise section. Then in the OpendTect attribute set, I've created a number of attributes that I cascade, and the final output of that is the filter applied with the weaker filter applied in the deeper section and the stronger filter applied in the shallower section. So here we see the mixed filter against the stronger filter, and we see that the mixed filter indeed preserves amplitude variations in this deeper section better. This shows how important it is to actually understand the data, and how convenient it is to have a number of tools that allows you to quickly test and combine different attributes. With this example, I conclude the demonstration part of my presentation. I just want to walk over some concluding remarks. Not going into the technical part of my presentation. What I think are the important things to remember from this is when you analyze data, apply filters, create attributes, keep thinking. Know your data and its characteristics. Know things: what is the bedding plane depth, what is the fault tip, what is the dominant period of the seismic data versus depth. Are there areas with these decreased data qualities, the data stationary laterally, etc., etc. Know how the attributes and the filters actually work, so you can make changes based on your knowledge of the dataset. Test, investigate, have attention to detail. As you see, in 20 minutes you get already quite far with this. If you spend 2 days, you have a significant uplift above just applying workflows with default settings. Keep thinking can be done in any software. OpendTect is particularly suitable for these kind of workflows, as it hosts a suite of filters, attributes and testing tools. It's very easy to operate, it's very quick to operate, and it's very interactive. In this 20-minute webinar, I have not able to show you even 10% of what's possible. So I want to point out that training consultancy is available to get you up and running with the software itself. Or there's always the possibility for us to do on a project basis work to improve a dataset for you. With that, I have reached the end of my presentation. Now we have time for questions and discussion together with my colleagues in the panel, and moderated by Marika.